Okay, the dreaded application problem. Alice rides her bicycle 24 miles in the same time that it takes Betty to ride 15 miles. Way to go, Alice. Good for you. If Alice rides her bike an average of 3 miles per hour faster than Betty, how fast do they each ride? Well, just looking at the structure of the problem, I know that we know what we should do. We should absolutely read the problem, understand what we're being asked for, set some variables, and we're going to do that. But we can agree that we could probably just look at this and maybe eyeball it, right? Because we can see that 3 divides into both 24 and 15. So if we were going to start guessing, it might be, we might be able to guess integers. So I really do want to caution you away from guessing like that. So guessing, it's a good idea. If we don't know what to do, maybe we could start taking guesses and structure ourselves from there. But if our main strategy is to just, take a swing at it and try a bunch of stuff, well, there are infinitely many numbers, and nobody's telling us that they each have to ride at an an integer rate. Maybe one of these people is riding 17 3/4 miles per hour. It's not like we're going to guess that, we're going to guess integers. So that's probably enough talking about telling you not to guess. We really want to take a structured approach at these problems anytime we can, just to streamline ourselves and do the same thing every time. So let's go ahead and do that. So we've got the problem. We've got 2 ladies that they're riding their bike. This one goes faster than this one. So it's a distance, rate, and time problem, right? Uniform motion. So anytime we have a uniform motion problem, that is distance, rate, and time, we can see the distance, rate, and time in a couple of different settings, but here it's clearly distance, rate, and time, right? Maybe we've got 2 people that are painting a house, or 2 people that are mowing a yard. Those are still distance, rate, and time problems, but the distance wouldn't be miles. The distance would be like the whole house, or the distance might be mowing the backyard or something like that, or a job, something like that. But anyway, here we've got pretty clearly distance, rate, and time. So anytime we deal with something with a known relationship, we ought to use that relationship to our advantage. So we know, we're just going to put this up here. We know that distance is equal to rate times time. And this is just known. This is just something that we know. All right, so Alice rides her bicycle 24 miles in the same time it takes Betty to ride 15 miles. Great. If Alice rides her bike an average of 3 miles per hour faster than Betty, how fast do they each ride? So we want to identify our variables first. So how fast do they each ride? So we want to set variables for these things. We want Alice's speed, and we want Betty's speed. We ought to be really careful for units. We're dealing with miles, we're dealing with hours, miles, so everything's standard. We ought to use miles per hour because that would make the most sense here. So we want to choose one of these to be X, and we want to use one variable if possible. And we can see that one of these things, Alice rides her bike an average of 3 miles per hour faster than Betty. So if we say that Alice's speed is X, she's faster than Betty by 3 miles per hour. So Betty's speed is going to be 3 miles per hour slower. So X minus 3 is going to be Betty's speed. So we're going to take Alice's speed and take 3 away, and we're going to get Betty's speed. Now we also could have said Betty's speed is X, and then we would write Alice's speed would be X plus 3. But it's going to end up giving us the same solution either way. So we can get away with just doing this. Okay, so we've set our variables. That's wonderful. What we want to do with this is we want to make ourselves a nice little chart. So we can write up a distance, rate, time statement for both of these ladies. So if we have Alice and Betty, they're both going to have a distance, they're both going to have a rate, they're both going to have a time, right? And we can just, la-di-da, make our nice little chart. And maybe put one down here just to be complete here, so it looks all beautiful. How nice. Okay, so we can fill some of this stuff in, right? We can look at the nice problem. We know Alice rides her bicycle 24 miles in the same time it takes Betty to ride 15. So Alice rides 24 miles, and Betty rides 15. Okay. Our rates, those are the speeds, so we've got those right here. Alice's speed is x, Betty's speed is x minus 3. Okay, and what about times? So this is the part where the chart, I think, is really useful for us because we don't know what this is, right? We might be tempted to put another variable in there, but we do know that whatever we write in here, we're going to end up saying that these two things are equal, right? Alice's time has got to be the same as Betty's time because that's the structure of the problem, right? Alice is riding her bike in the same time that it takes Betty to ride 15. So at the end, we're going to end up setting these two things equal, whatever they are, so we can find them, right? Because if we have a relationship between three variables, if I told you any two of these variables, you could give me the other one, right? If I gave you a rate and a time, you could tell me the distance by just multiplying. But we're giving you the distance and the rate. Well, we're not really given the rate, but we have distance and we have rate, or at least an expression for the rate, right? So if we had these two things, if we wanted time, well, we can just take our nice little formula here and divide both sides by rate. And this is still true, as long as the rate's not 0, but that's kind of a silly situation that we're not going to be in. So here is what we're going to put here, right? We've got distances for each, we got rates for each, and let me write this in red. So we've got distance over rate, so 24 over x. Down here we've got distance over rate. Okay, so now if we knew what Alice's speed was, I could tell you Betty's speed. And if I knew either one of those things, I could tell you either one of their times. Well, we don't know either one of those things, but we do know that these two have to be equal, right? Because they ride these distances in the same time. So if those distances, if those times have to be equal, well, this has to be equal to this. So we can write, well, let's write it in words first, right? Alice's time has to be equal to Betty's time. I don't know. When I'm doing application problems, I try to write things out in words as much as I can in my work because it helps me make more sense of it, I suppose, if we're writing out in words what we're doing. I guess we're not doing too much complicated with words here, but use English as much as you can because we're comfortable with that, and then translate it into math as you go. So we got Alice's time, boop, has to be equal to Betty's time. Bob. And now we're off to the races, right? We have a nice equation and we can solve the nice equation. So let's go ahead and do that. We know that whenever we have a rational equation, the first thing we ought to do is note what the denominators are. So these are going to be restrictions, right? I cannot have that x equals 0, and we cannot have that x equal 3. So if we end up down the line here saying that either x is 0 or x equals 3, we know that we screwed it up. We know that we should start over, or not start over. We know that we got to throw those solutions out, rather. Excuse me. Those are extraneous if we end up saying that these are solutions. Anyway, let's get on with it. We know what we're doing. So we've got a rational equation. Usually what our strategy is we want to multiply everything by the least common denominator, which is x times x minus 3 in this case. I'll multiply that on both sides. Okay, so now when we multiply these, we're gonna see that the fractions go away, right? So x divided by x is just 1, so that goes away. We got 24 times x minus 3. And over here we have that the x minus 3 gets canceled out, so we have 15x. All right, so that's nice. That's a nice linear equation there. We can deal with this pretty quickly. We would just do the regular stuff, right? We're going to distribute the 24. So we got 24x minus 24 times 3. What's that? 72. And then we have 15. X. That looks kind of like a Z, doesn't it? Okay, and we know what we're doing here. We can solve this. So we add 72 to both sides. We're going to take 15 away from both sides, or 15x rather, and then we can divide by 9, and we can see that x is 8. Okay, and then we have to go back and see what x even was. What did we set ourselves up as? Okay, Alice's speed was x. So this is Alice's speed, and we can probably tack a unit on there, miles per hour. This is Alice's speed. And then we wanted x minus 3, so that would be 8 minus 3 is 5 miles per hour, and that is Betty's speed. So we've got Alice's speed as 8 miles per hour, Betty's speed is 5 miles per hour. So back to what I was trying to say at the beginning, we can see, you know, we probably could have guessed these, right? If we would have taken and just, you know, do the natural stuff, like what do you want to do with numbers? You want to add them, subtract them, divide them. If we would have just divided both of these by 3, we could have guessed this and then maybe checked it and, you know, guess and check, right? But we've got to understand that there are infinitely many numbers that we can guess. It's not a coincidence that these numbers worked out to be like this. When people make these up, they usually pick values that will work out nicely. And that's what I did here. You know, the numbers worked out nicely because they were supposed to work out nicely. Now, if the numbers don't work out so nicely, you're probably going to have a little tougher time guessing at your solution. So do yourself a favor, make the nice little chart. When we have the known relationship, and you will enjoy that a little more than guessing at infinitely many numbers.